is here in 2D and also the pressure. And here you have too many unknowns. It can't be solved alone. So what do we do? The basic philosophy is actually the same as what we had with the Sol algorithm, the projection method or split step method. You calculate a velocity based on something wrong, maybe old pressure or not low pressure or whatever, and then you have to use somewhere along the line the continuity equation. And we have one unknown too many with only the momentum equation, so continuity has to be used somewhere. And the classical solution, which we all should know about, is called semi-implicit method. And then for pressure linked equations. And that should now spell out to be called simple. Semi-implicit method for pressure linked equations. So we have our first equation now, an algebraic equation. On the classical form, coefficient for the node P multiplied with the unknown there, a velocity U, equals, and then you have a whole bunch of neighbors. Sum of all neighbors and the unknown for all the neighbors. Something like that. And then we will have plus, and then some pressure. Delta P or just P multiplied with some coefficients there as well. And finally, if you want, you can have a constant source term there if you like. So here we have equation number 1. And now we solve this equation by introducing something wrong. We don't know this pressure, he's also an unknown, so for this one we guess something wrong. Pressure star. So yeah, then we can find a solution for U and the same with V of course, but it will in general then be wrong. Then we correct. The correct pressure should now just be called P. P will be equal to the one we guessed, P star, and then plus a correction, P stroke. So here, the pressure correction. So now we are actually seeking an equation for how should this pressure correction look like. We also introduce corrections for the velocities. So we have U and V as well. And also here we have something wrong. This is what I call the tentative velocity field in the split step method. And here U stroke, V stroke. So equation number 2. the one we can solve will now look something like this. This wrong velocity field. So then, based on all these neighbors, neighbors. Star, and then we use delta P star, and finally plus B. So that is equation number 2. So you might say equation number 1, that's the one we would like to solve, but we can't. Equation number 2, that's the one we can solve when we use something wrong, the wrong pressure. And typical the pressure from the previous iteration, or if it's a transient code, the pressure from the previous time step, something like that. Now take the difference between these two equations, so you'll have that one, equation number 1 minus equation number 2. And we will end up with something like this. Same coefficients, but now the real u minus this u star, meaning we have only the velocity correction. So that's nice. Equals, and then here we have the sum of all the neighbors, u neighbor, and also correction. It's the real one minus the star, so this is quite okay. Same goes with the pressure, plus whatever we have, delta P fluct. The constant B, he will now disappear. So here we have an equation sort of giving us the velocity correction. Well, we can write it. Oh, leave it. And then we start to do some dirty tricks. I say that this one is 0. And then you should say, hey, oh, whoa, whoa. Of course it's not. So there we are talking very semi. It's going to be very semi indeed. So he's not 0, of course, but we do it anyway. So if we now take our equation for the velocity, and now we rewrite him a little bit. Let's see if we take this one. So I want the correct velocity, up, equals this up star, and then we should have the velocity correction. But I don't want to use the velocity correction, I want to use the pressure. So here I will have something like 1 over AP multiplied with this delta P correction. Still doesn't help me. I have still one equation with 2 unknowns. So finally we have to use the continuity equation. So for the continuity equation, here on a conservative form, you will have the time derivative of density, x derivative of rho u, y derivative of rho v equal to 0. And then I take this one and insert for the velocity. And of course you do the same also with v. So you substitute in for the correct velocities, and what are you left with? Well, this will now be an equation involving these tentative velocities, which was easily found, no problem there, and the pressure correction only. So this one will give us an equation for the correct, which is the one we are seeking. So you solve the continuity equation, or actually use the continuity equation to find an expression for the correct pressure adjustments, and then you insert and you guess again, and you do it again, finding new better velocities to be inserted here, finding a better correction, and so you continue. So this will sort of be the recipe for simple, the classical simple. And since it's semi-implicit, yes, you have to iterate. You can't solve it directly. If you had kept this, don't say that this is 0, okay, then you would have ended up with a direct method in the end. So somewhere along the line here you have to choose. So the sort of the first success, that was this simple, how to solve this pressure linked equation systems, velocity and pressure. Yes, and it works. It's slow, it's bad, but it works, and it's quite robust. Also, what's good with it is that you will always have continuity, no matter what you do. So you can end up with something totally crazy, but at least the continuity equation is going to be fulfilled, no matter what. So that is sort of one advantage here. How this equation actually looks like will of course now depend how you discretize this continuity equation. So many ways to do that. After this one was invented, you immediately had a whole family of variants. Some of them quite smart actually. One, for instance, is called simple say. You do this equation here, but you do a trick. You rewrite it a little bit. So you have the coefficient here, AP minus the sum of all the neighbor coefficients only, multiplied with UP correction, equal, and then here you will now write the sum of all the neighbor coefficients, and here you will now have the difference between all the neighbor velocities, correct, minus the one we are seeking, and then delta P, and maybe some coefficients there as well. So first glance, this doesn't help much, but when you now do the dirty trick and say this one is 0, of course, still, wrong, still semi, but closer to 0. Since we have a difference in velocities. So very little trick, but helps the convergence rate a lot. So that's just one trick. You have several of these: simpler, simplest, simplex. I don't know all the versions. So you have many variants. But the philosophy is just this. And it's possible here, if you go through it with a rectangular cell systems, don't use triangles, but just use straight rectangles, uniform mesh, you will see that this method is identical to the projection method that we had with finite difference. It's exactly the same. So, of course, they are in family with each other. Any questions to this one? Sort of the essence with the finite volume methods. This is hard to avoid. Nowadays you have also more sophisticated methods, but some piezo algorithms using corrector predictor idea here as well, and then some additional correction terms, but I would say the heart of the method is here anyway, so of course you have variants of it. That's okay? We have some more dirty tricks you should be aware of. Let's see. Look at one momentum equation here, written in this Pattankar form. Time derivative, rho phi, convective terms, rho u phi, equals, and then you will have the x derivative of gamma x derivative, and then, no, not that phi, maybe a source term here. And in finite volume, what we do, you take the integral of from t to t plus delta t, and you take the interval of some control volume from west to east, if you use Patankar's notation there. And you will end up with something like this. This one only be, make it simple here, east-west makes 1 delta x. And you will be left here with the difference from time level n to n plus 1 of this term. This one will now be something like, what will it be, delta t, and then rho u phi from west to east, and this one, oh yeah, okay, should now read something like, well, he's not a problem actually. So starting with the dirty tricks. Here you can stabilize a lot by use the old density instead of the new one at the new time level, at least the first time. You have to do this some iterative anyway, so you have to cheat a lot. Also, a stable trick, use n plus 1 here. So it will now be a little bit more implicit. also tends to stabilize. And also what people do, you add 0 to the equation. And the 0 looks something like this, Vn plus 1, and then the volume integral of d rho dt plus x derivative of rho u at time level n plus 1 dx. Now this one is a 0, but if you do it, you end up with a much more diagonally dominant equation system in the end. So people do a lot of these, say, dirty tricks without actually giving them much argument why, just that it speeds up the solution process, and that's what we are interested in. So it's possible here to play around with these equations a lot. So people have tried and failed a lot over the years. So today we have a good package of decent operating algorithms that actually works, but a lot of them will be based on some dirty tricks that people actually don't talk too loud about. But they do things like that a lot. They cheat a lot. But I mean, this tentative velocity field, for instance, is going to be wrong anyway. So if you add some more wrong, who cares? It shouldn't change anything. We have to adjust it anyway. So if you can find a smarter way to make these adjustments, okay, that's good. So not everything here can be sort of numerically validated and argued for, and this must be a good idea. But in the end, some of them might be a very good idea. So like this one, this then gave a more diagonally dominant equation system. Yeah, I won't go through all these different dirty tricks and all the different variants and methods that exist. So this you have gotten some idea what this black box contains. A little talk about meshing. Nowadays you will have a nice piece of software and you put in your geometry somehow, typically from an AutoCAD file or something, and then you click the mesh button and then you don't have to think of it anymore. But say in general, a structured mesh will be better, faster, more accurate than an unstructured mesh. So if possible, try to avoid it. Can be hard, of course, but for instance, for such a problem, typically what you will do, you will have a mesh layer to resolve the boundary, and that will consist now of structured mesh systems like this. Can be 5, 6, 10 cells thick, but you have a rectangular, more or less, grid system, a structured grid system close to your boundary. Very good idea. And then outside, you are not so worried about the solution, it doesn't have to be too accurate. So now you can start with using unstructured meshes, for instance, and making bigger and bigger cells to find a solution. So that should be quite possible. And you will have methods dealing with just these problems. But I mean, before you do something like this, first test case. Take a two-dimensional flow between parallel plates. Use periodic boundary conditions, and the flow is laminar. Then you know the solution. It's going to be the Poisson velocity profile here, So wherever you are inside that domain. That one is analytically, and you know the pressure gradient should vary linear from P1 down to pressure P2 on the other side. So the pressure drops linearly. And then you test your fancy, expensive CFD systems. So here you now use nice Cartesian rectangular cell system, and then you have a region here where you now use unstructured mesh systems, and it can be more or less dense, up to you of course. And then I'll take another layer here, some triangular systems, and then you go back to the Cartesian. Do that as a test case. Take just a region with totally unstructured mesh, more or less dense. Play around with it, see what happens. You know the solution. When you now plot the average pressure gradient, it should go like that. You shouldn't even see this in the solution. So it's a hard test, but you should definitely do it before you are jumping into your own real problems. Then you know he can handle it. I mean, if he can't handle this one correctly, then forget it. It's that simple. Of course, he should handle it. You also have another philosophy with refining mesh close to your area of interest, where you have sharp gradients. Then you will do something like this. Have a mesh system here, and all of a sudden you start splitting the cells. Like this. Of course, in terms of finite differences, then we would say, hey, ooh, this is not possible. I mean, you have one cell here, like that, and then you have 4 neighbors in the plane, but all of a sudden here we have 2. Well, that's not so easy. So for the cells to the right there, they will now require input, say a velocity here and a velocity here. But from the big cell, well, maybe we have the staggered system, so we only have velocities on each face. So you only have one velocity here. Has now to be split into 2. Okay, then you need some interpolation tricks to do this correct. And yes, they exist. But my point is, before you start using it, you do such dummy test cases like this and see what happens. A nice rectangular mesh, and all of a sudden you start to refine it or split it up or whatever, just to check that you have the correct pressure gradient between those 2 parallel plates. Very easy test to see if we can handle something like this. Other problems you may encounter when it comes to the meshing. Say you want to do a 3-dimensional pipe flow, and then sort of without thinking, without saying it out loud, you will definitely here jump to cylindrical coordinate systems. So you will use something like this, and then a mesh in the radial direction and in the theta direction. Of course you should, and then you have a nice structured mesh system. But say if this one is a pipe flow, 3-dimensional pipe flow, and you make a bend, or you have some geometry that change it a little bit, so you will have velocities here in the cross-stream direction. Okay, then what happens? Take one of these innermost small pi cells. If you have many cells in the theta direction here, they can be quite narrow. So now, if you have one velocity here, say in the cell center, going in the theta direction, one small little v theta, he can jump over many cells when he is close to the center here. which is going to be very, very expensive if you think in terms of the Quadrant-Friedrich-Levy number. You should not pass more than one cell length during one time step. Okay, then you are asking for trouble. You can't do this. It's a very bad idea. So what you do? Well, you can use cylindrical coordinates here towards the inner surface of your pipe. That's okay. But in the center, you switch. Use unstructured mesh or some hybrid mesh or something, so you sort of end up with a more or less rectangular mesh system in the center, or else you're dead. Finally then, if you are talking about moving meshes, you have a part in your domain that rotates, is moving. Then you are quite dependent on handling such problems like this correctly. Because what you do then is to create one mesh system here, say following the thing that rotates, say if it was a turbine or something. So you create one mesh in a circle around the rotating object, and then you have another mesh outside which now is fixed. So that means you will have sort of a sliding mesh line here, where you can have cells which now will have any orientation in regard to the fixed mesh. But of course then this type of interpolation will be quite crucial when he slides. But that is how you can handle moving parts in your problems. Not easy, but yes, possible, if you do such simple problems like this correctly. Any questions to that one? Anyway, then tomorrow we will then start with turbulence. I will put out some material for you on the homepage, so you can have something to look at there. And then we still have time before Easter, so then it's a question, should we play around here with open foam? If I set up a crash course here with open foam, how many of you will be interested? How many of you will show up?
But when is it going to be? Because
we still have time before Easter. I mean, the turbulence should be finished not tomorrow, but at least next week. So we can start next Wednesday, I guess.
I'm interested, unfortunately I'm not here.
You're not here, okay.
Will you video record it also? Will you video record it also?
Sure, no problem. That's very easy. But I mean, you need hands-on and you need a computer.
That'll be in next week.
And next week, I think we can start, yes.
Oh.
With open foam. Nothing to do with the exam, so this is just for volunteering anyway. But as an information, I think you should know about open foam, because that's one decent CFD software that is totally free. You can make money out of it. You can create your own company without having to pay the licenses. So it's a good idea. So okay, I will set it up. Then you have to prepare your laptops. And of course you have a laptop, and of course you don't buy Macintosh. Nobody has Macintosh, right? Why? They don't work. It's possible to make it run on the Mac, but it's hard. You have to install some virtual box to run Linux.
I have also VirtualBox.
You have it already?
Yeah, not Macintosh, but it's Windows.
Okay.
I use Linux.
So what I normally do, I prepare a USB stick. So you insert that USB in a laptop, and then you boot on the USB. Then you have a Linux machine.
It still only compiles on Linux, right?
No, you have a Windows version, but it's terrible. It's slow and also no, we don't use it.
Yeah.
I have one version where actually a company gave me some licenses. They have made an umbrella over OpenFOAM in Windows. So I think I still have that one operative. I have to check with them. So that's an alternative. But that is more, I don't like it that much. It's more like the CFD thing. It doesn't blow up as easily as it should. I prefer that the code blows up when you do something stupid. But I'll see what I can handle. But the rest, if you have Windows laptops, check that you are capable of booting on a USB, an external hard drive. So you have to set up, go into the BIOS, and that might not be so easy on a modern machine. Bill Gates don't like that you use other operative systems than Windows. So some of them maybe actually have some, they are prevented to do that. But if you hack a little bit, Google your exact machine type and see, can I boot on an external USB? How can I set up my BIOS to do that? Then it should be okay. So see if you can deal with that until next week. If you have problems, see if you can borrow an old one. And then preferably a very old one. I mean, an old laptop will actually be quite fast when you run Linux on it. Linux is a very good operative system, so if you haven't used it yet, it's about time you get things started. So Linux is a good one. Yeah.
Yeah, just as a comment, it's pretty easy to install a VirtualBox as well, so that might be
Yeah, the problem with VirtualBox is then it's going to be slow. And you'll have, well, it's not a problem for us, you'll have some memory limitations, but you don't get the access directly to all your hardware. So you have to go through the system, but it
I don't
works.
really agree, but okay.
I think with direct CPU access, the graphics is going to be slow.
Yeah, something like that.
I think VMware it's better than the VirtualBox.
VMware is better, but then you have to pay the license. We have licenses on VMware, we have at least, but check it out. But it should be possible, I mean, to borrow a computer for a few weeks, especially an old laptop. I have at least one I can borrow.
There is no commercial also version of the VMware, but you can download from their website.
Yeah, they have some free version.
Yeah, I use it. Yeah.
Okay, and it works?
Yeah.
Okay, good.
Yeah, it's better than VirtualBox.
That I can believe. Okay, so check it out. See if you can borrow a laptop and bring it on. It should be. Well, we see tomorrow how far I can get with the turbines. Okay. Just for the last part here, I won't go through the details, quite boring. So the simple and simple C and simpler is briefly discussed here. Also the different stencils then required when you do this uneven numbering. Have a big triangular system with the pressure and velocities, and then a smaller one in addition with just the velocities. Simple C, yeah, listed here. And the second part, well, we have another variant, call it an equal order control volume finite element. And the recipe is practically the same, so don't bother going through the details here. Talk a little bit about jumping into 3 dimensions. And as I said, normally what you will try to do, if you have a nasty geometry, at least see if you have one direction where you just can use the same mesh. So you sort of extract your complicated unstructured 2D mesh into 3D. Because jumping into pyramids and formed shaped elements, that's massive, slow, expensive. So if possible, try to avoid it. Yeah. So there are a lot of references here in the end. Yeah. So you can look at it. And also the appendix, where actually I found the equations that I just tested, programmed it straightforward, no problem. So the method seems to be working quite okay actually. Okay, then turbulence tomorrow. Any questions from you?
Excuse me, I have
Yeah.
a question about the periodic boundary condition.
Yeah.
If we have a channel and there should be, for example, sand water that flows through the channel, we can, if there is precipitation in the downstream, then we can use a periodic boundary condition.
Careful. Careful with that. You said you had a channel and you wanted to use periodic boundary conditions here.
And the channel has the corrugated wall, and in each part it's a repetitive structure.
Okay, so you have something,
Yeah.
but then it will continue like
Yeah.
this. Yeah. So you only take one bump or
Yeah.
something. Yeah. Yes, that is quite obviously. Yes, you can take periodic boundary conditions. How you want to do it, your choice. To take it in the center here, in between, from center, min point, or if you took it from the top to the top, or if you took it from any location, it really doesn't matter as long as it is the same. So you could have taken a mesh, say from here, all the way up to here, and said, yes, this is one period. Yeah, of course you can, no problem.
Even if we have precipitation of the salt in the downstream, because of this vorticities that's behind.
Yeah, you mean you get some
Yeah.
vortex here, and also you'll have some noise here as well, and it's, I guess it's turbulent, so you can have a nasty. It's not easy, and also I would say it will be transient here. So it's only 2D, not 3D.
Yeah, in 2D, but it will be somehow laminar on the top, but around this will be turbulence.
But if you do the cyclic boundary conditions correctly, it's not should work just fine if you take straight through all this messy behavior. Shouldn't matter at all if you do it correct. So I mean, you will map whatever goes in, or if it goes out, it doesn't matter because you map it over here anyway. So yes, that should be quite okay. And for your equation system, it really doesn't matter where you put your boundary. So that shouldn't be any problem at all.
This is only true for dance models, right? I mean, 3D
No.
obviously.
No. This is true for DNS, LAS, whatever.
Yeah.
We'll address this one a little bit more when it comes to the DNS and LAS, because that is a headache, the boundary conditions. But periodic, they are fairly easy. What's of course dangerous here, if you had a system, a physical system, say if these were quite close. So you will have structures spanning over more than 2 of them. Then you're in trouble. Then you have no choice. Then you have to simulate the whole thing. Because then, if you have structures here, a long turbulent structure of some kind, that spans over your entire domain, you just feed it unphysically, you send it in again. And that's not correct. So your domain sort of have to be big enough in order to do this. That will be not for only DNSs, but also for any code, even laminar flow. If you take periodic boundary conditions in a too narrow problem, then you will just physically feed some strange structures which shouldn't be there. So that depends on your problem. But I believe if you have a decent distance between those two here, no problem. No problem. So, but I mean, it's, for you, then it should be possible. Take 2 and then make a boundary condition, periodic boundary conditions. Should be the same. And then see if you get any differences. You shouldn't. Of course, you have to double the amount of cells, but still possible. So that's an easy check for you. Do I have such long structures that sort of is going to interfere with my boundary conditions? Okay, double the cell and take it all the way up here and see, does it change anything? No? Then you're good. Other questions? Then I'll see you tomorrow.